Here in this module, we're going to focus on modeling with higher order differential equations. In previous videos, we saw a single differential equation can serve as a model for a diverse set of physical systems. Now, for this reason, we're just going to focus on one application in this module. Except for terminology and physical interpretations of the four terms found here for this second order differential equation that's also linear, the mechanical spring mass system is identical to that of an electrical series circuit, and in this module we'll deal exclusively with initial value problems as shown here. We'll start off with this module concerning about linear models focus on initial value problems. Here we'll start with going to consider several linear dynamical models or systems in which each mathematical model is a second order differential equation with constant coefficients along with their initial conditions. So shown here is a second order differential equation, and A, B, and C are the constant coefficients. Here G of t is known as the driving or forcing or input function associated with this differential equation, and Y of t is the corresponding output response as a result of the forcing function as well as the natural response or homogeneous behavior of the system. We're also given initial conditions for the y of 0 and the first derivative of y with respect to time as initial conditions. We saw in an earlier video that undamped motion can be found in the string example, where this can oscillate forever and ever, where we have no damping. So let's look at this spring mass example in which we have three springs here. We'll just take a look at the third spring, and this is, we'll see what the undamped look case, and that deals with the air friction associated with this simulation. So when you have no friction, no air resistance, and we oscillate this by pulling this force down on the spring, we see that it will oscillate forever and ever. Now this corresponds to a characteristic equation having purely imaginary roots, so it's a combination of sines and cosines as our homogeneous equation to this with the forcing function. And here when we apply lots of damping, you could see that the motion stops, and this is a result of the real part being dominant over the imaginary part where it's oscillatory. So the oscillatory behavior is due to the imaginary part